Okay, someone said something. May I know how to solve dy del where del by del y del f f double dot by f dot. This one. We are not solving this one, right? We use the instead of writing d by dy del f double prime by f prime, we are writing d by d eta f prime by f prime multiplied by d eta by dy. We use the chain rule. We are not using d by dy. We just write d eta. D by d eta, the f double prime by f prime multiplied by, then we have d eta by dy. Okay, because f is a function of eta, not y. We use the chain rule. You see? Oh, I haven't said that. Everything cannot be written. Okay, sometimes I also say that this one. You see, is already there. D eta by dy. I'm not writing d by dy. Then d eta by dy. Chain rule. Differentiating with respect to eta, but again differentiate eta with respect to y. Eta is a function of y, no problem. F is a function of eta, no problem. So I can solve the problem. Okay, so I just continue. We don't have enough time. If I left these things, very difficult to continue. So what I said that now you have this x is equal to 0, your g becomes infinity. So if it becomes like this, your c is actually 0, because g infinity means g minus infinity. 1 by infinity is 0. Okay, so x is 0, so c should be 0. So if your c is 0 here, what you will get? You will get g square is equal to minus u infinity 2k mu x. Right, yes, right. So in this case, your k is a constant, right? K of course should be negative, okay? Because g cannot be negative, is a square. It should be positive, so k must be negative. So let's consider again, for our convenience, k is minus half. Is minus, okay? Very big minus. Okay, so if it is minus half, what you will get? So your g will be root over of u infinity, then half of will be cancelled out. You will have mu x. Okay, so half of will cancel out, minus minus will gone, then you will have u infinity by mu x. Oh, someone left already. So your g is this one, okay? So your eta is y gx, right? Yg. So y multiplied by u infinity by mu x. Remember, your eta is y root over of u infinity by mu x. Okay, so you already got some result. Your the eta the expression for eta, and then so we consider the other part. It means we consider this much, this one already left, right? We just derive this one is equal to k. So how about this one? So now let's consider the other part. So this should be other part. Other part we will have 1 by f, and then we have d eta, we have f double prime by f prime should be k. K in this case, in our case, is minus half. So what we will have, d, we have f double prime f prime should be equal to half f d eta. Okay, just shuffle it. Then what we can do, you can see here we have the d f double prime by f prime is equal to 1/2 and f dy. So actually we are reducing the PDE to ODE. Okay, so we are reducing the PDE to ODE. So let's consider in this case integration of f d eta is equal to capital F. So we need to integrate, right? If you integrate this one, let's consider integration of f d eta is equal to capital F. So you can write that d capital F d eta is equal to small f. It means if you differentiate small f, you get capital F. Sorry, if you integrate small f, you got capital F. Again, you differentiate capital F, you got small f. So it's already the integrating constant already taken into account. Okay. Now I do the integration. What you will get here? So you will get that integration of d. So now I already changed the small f to capital F. Okay. So you can understand that now I don't have the small f anymore because I am changing the variables. So I am making the ODE, PDE to ODE. So in this case, your f prime is actually small f. If you consider the derivative of this, okay, it means this one, right? Capital F prime is this one. So f double prime will be small f prime. So just do it like this, and f triple prime will be f double prime. So what you will get from here? So you will get that integration of d f triple prime divided by f double prime is equal to minus half capital F. So integration and derivative term will be cancelled out. You will get what? 2 f triple prime plus f double prime is equal to 0. Okay, now you have this ODE that you can solve. This one you can solve. Okay, so I reduce the momentum equation to this form. Now this one can be solved numerically. Okay, this one can be solved numerically. Now I go back to the slide. Okay, so they do lots of things, but it's not clear. So that's why I try to derive it properly. And at last, you will get the same here. But here they use small f, but it should be capital F. Otherwise, it's confusing. Okay, so you can see that we have this 2f triple prime plus f double prime should be 0. So then, if you want to solve it analytically, okay, numerically, if you solve this problem, so we found this one. So Blasius tried to solve this problem, and using the f eta, we try to find the solution. Okay, so in this case, your eta, as I said, that eta is equal to y g, and g, you remember that u infinity and divided by mu x. Okay, so is already there. And then f, in this case, f is what? In this case, f is actually capital F prime. Okay, and how about f prime? Hold on, mix up. I'm sorry. This is small f. Okay, this is actually not small f. It should be capital F. According to my derivation, it should be capital F. There is no small f in your equation, right? So you have the eta. You change the eta value, and then you will get the solution, because f is a function of eta, right? So f is a function of eta. You change the eta, where eta is y root over of u infinity by mu x, and then you will get the value. This is capital F. It should be capital F according to my definition. So this should be also capital F prime, and this one capital F double prime. So f means, as I said, your f capital F in our case is integration of f del eta. You just get the values, and f prime in my case is f, small f, right? And if you remember, what is small f? U is equal to u infinity into f, right? So f should be u by u infinity. So this column is actually doing the same. F prime is actually small f, and that is u by u infinity. That is the ratio, right? So this column is very important. This column is important. This represents f prime. Capital F prime means small f. Small f means u by u infinity. It means the velocity ratio. And this one is a f double prime. Is f double prime means actually your f prime, right? So now if you change the value of eta, okay, I try to do it faster. If you change the value of eta 3, 4, 5, something like that, you focus on here, velocity ratio. So it finds that when the eta is 5, your velocity ratio is 0.9915. It means your velocity reaches 99% of the free stream velocity. That is the condition for boundary layer thickness, right? So it means that whenever your n is 5, you got the boundary layer thickness. It means you satisfy the condition for boundary layer thickness. So this is the bigger form, okay? So this is your breakthrough. So it means when your eta is 5, your velocity already reaches the condition to justify the boundary layer thickness. So it means that when n is equal to 5, sorry, eta is equal to 5, your ratio is this one. So you can write in this way. So in this case, you can write your eta is equal to, as I said, y gx, g is root over of u infinity by mu x. So when n is equal to 5, your y will become delta. That is the thickness, right? So if you just put it here, your 5 and delta and root over of u by mu x. This is u infinity. So this one can be represented or can be written as delta is equal to 5x root over of Rex, Reynolds number. Okay. So normally how they just do some simplification. For an example, they write in this way: 5x should be equal to delta root over of u infinity by mu x. Then we have x, you multiply both sides, but x in this case they write root over x. Okay, then you have the 5x here, and delta should be, you can see the root over x, one root over x will be cancelled out, and you will have root over of mu u x by mu, that is Rx. So R means what in this case? This one, right? So you have root over of means you will have root over of this. So root over of this one, you have the root over x do inside, and this the lower one, the root over x, will be cancelled out. So if you do the simplification in this way, you can write delta is like this. So your boundary layer thickness is 5x is the position divided by root over of Rex. So this equation is known as Blasius form to calculate the boundary layer thickness. Okay, this is the form to get the boundary layer thickness. Similar way, we can consider the displacement thickness. So in case of displacement thickness, you know that this is a relationship, right? Delta star root over integration of 0 to delta 1 minus u by capital U or u infinity dy. But you know that your y is actually eta root over of, and we have mu x divided by u infinity. I just shuffle it, okay? We know that eta is equal to y by this one, so y is like this. So dy should be d eta root over of mu x by u infinity. Okay, or you can write in this way. This one again, just shuffle it. They write it in way. So this one y cannot be there, so you just replace the y by eta. So you have dy is equal to d eta x by root over of Rex. So dy, just put the value here. So this should be x by root over x. This is constant outside, and the delta is here, and u by u infinity is actually what? So you remember u by u infinity is actually capital F prime. So you need to write capital F prime in this case. There should be no small f, okay? So you need to just little bit modify. This should be capital F prime. If there will be no small f according to my definition, okay? So just integrate it. This should be eta, and this integration and differentiation will be cut down. You will have only f capital F eta, and simplify it, and you will see that the value is this one. This is the value, okay? Just you make this one eta f eta, and then you need to substitute the value. Eta should be 5. Eta will be 5, right? And what is f eta? You need to go back to the table. Your f eta means this value. As I said, these are capital F, right? Capital F prime, capital F double prime. So you need to put this value for displacement thickness for the same situation. So if you put the value there, 3.2833, you will get this value. So this is your displacement thickness expression for displacement thickness. So if you just put the value of x and you have the Reynolds number, you will get the displacement thickness. We don't have enough time, but this one for the momentum thickness, similar way, this expression is same. We have this expression x by this one, we have this all capital, okay? So in this case, momentum thickness, we cannot have exact solution. We cannot have exact solution because we have multiplication of both. So so we need to actually solve it numerically, okay? So it just said that the equation in the integral, we have these coupling terms cannot be integrated analytically. So for eta greater than 5, this will not change that much, and that will be equal to 1, and the numerical result is like this. Okay, so it means that it's f prime eta. They say that when we integrate after 5, there will be no change. You can see is almost 1. So if we consider it 1 and we do the numerical integration, and so we will get the result in this way. So your momentum thickness is this much. Okay, and there are some other equations, solutions, exact solution. You just need to remember like this, okay? So your stress tensor will be like this. Your local screen frictional coefficient is like this, and then we have the average friction is like this. So we have different values. Okay, so all the expressions actually are related with the Blasius form. It means solution of the Navier-Stokes equation. Okay, that's all because it's already time.